Jai Hind. The topic which we are going to discuss today under blockchain architecture subject is consensus algorithm, and basically we are going to discuss consensus algorithms in permissionless blockchain environment. We have already seen that there are two categories of the blockchain. One is permissionless blockchain and another one is permissioned blockchain. When we talk about the permissionless blockchain, then this implies this is an open network. Anyone can come and join the blockchain network, whereas in the case of the permission blockchain, it says that only the validate or the authorized individuals, they can join the blockchain network. So in a permissionless environment, there is no central authority who is authenticating or validating the users, whereas in the case of the permission blockchain, we are having an authority who is validating or authorizing the users who can access the ledger in that particular blockchain, and that particular person is also deciding whether that person user is joining the network as a simple peer node or as a miner. So today we are going to discuss the consensus in permissionless blockchain. So what is a permissionless model? As I just told you, that it is an open network. Anyone can join the network and initiate the transactions in this network. The participants, they are free to leave the network and they can later join the network again. So here there is assumption that is more than 50% of the participants are honest. This is the assumption we are taking, because if we don't work on this assumption, then the blockchain on which we are operating is a malicious blockchain which is being operated by a set of attackers. Why we have adopted this assumption? Because we are aware that a society cannot run if the majority of the participants are dishonest. So this is the assumption which we need to take in the case of the permissionless environment, because it is an open network. Now the question comes, what is a consensus algorithm? As we are aware that in this environment or in the blockchain, we are not having any central authority which can validate or verify the transactions. Yet every transaction in the blockchain is considered to be completely secured and verified. So this is possible only because the presence of an consensus, that is an agreement protocol, which is a core part of any blockchain network. And also the parties or the users who are operating on this network, they are not the trusted party. They don't trust each other. For example, this is a blockchain network. We are having 4 nodes, and these nodes, they don't trust each other. Now when this particular node initiates some transaction and this transaction needed to be added in the blockchain, then how these peer nodes, they will verify, they will validate this particular transaction and add this to the DLT, because they are operating in a trustless environment. So here we need certain algorithms, protocols through which these non-trusted parties, they come together, they make a joint decision on the basis of which this particular transaction, either it is going to be added into the blockchain or it is going to be completely discarded. So a consensus algorithm is a procedure through which all the peers of the blockchain network reach to a common agreement about the present state of the DLT. In this way, the consensus algorithms, they achieve the reliability in the blockchain and establish a trust factor among the unknown parties. So essentially, the consensus protocol makes sure that every new block that is going to be added to the blockchain is the one and only one version of the truth which is being agreed by all the peer nodes in this blockchain. So when we talk about the consensus algorithm, and since this consensus algorithm is being operated among the trustless peers, then there are certain challenges we need to be addressed when we talk about the consensus algorithm. The participants, they do not know each other, so there is no trust factor. So since there is no trust factor, and moreover they are unaware, this particular node is not aware to whom it is being connected, so it cannot use message passing on them. Also, all these peers, they are working in a anonymous environment. Also, then since there is an anonymity in the blockchain, so the message passing cannot be done here. Another challenge comes due to the fact that anyone can propose a new block. So who is going to add the next block in the blockchain? Suppose this is the person who has proposed a block. Similarly, this person has also proposed a block. And moreover, we are aware the set of transactions in both the blocks that don't need to be same. Suppose this block contains the transaction number 1, 50 and then 100, and this block, it consists of the transactions 1, 50, 101 and then 200. Then which block is going to be added in the blockchain? This is an important decision need to be taken, since both the users, they have generated a block, and users, they are saying that their block contain the validated, verified transaction. So now the question comes, which is to be added to the network first. Another important thing here is that the network on which this blockchain is being implemented is asynchronous in nature. We do not have any global clock. A node may see the blocks in different orders. Now what it says in different orders? Suppose this is a user. Here the block is being reflected in B1, then B2 and then B3. The DLT, we are aware that the blockchain the copies of the blockchain is to be kept on all the peer nodes. So this particular user is also having its own copy. This user is also having its own copy, and this user is also having its own copy. Now the order in which the blocks being added at this person may not be necessary same to this person and same to this person. Suppose here the order of block is B1, then B3 and then B2. Here may be the possibility we are having B3, B2 and B1. Although the blockchain, if we say the combined information in the whole blockchain, that is consistent at this and at this node, but still the sequence of block need not to be same at all the users. And what's the reason behind it? Because all the three users, they are working in the asynchronous environment. Suppose this user send a information to this user to add a block B3. Similarly, this user send the information to add the block B2. Now, whichever information is being received by this user first, the sequence of a blockchain, blocks within the blockchain depend on that order. If this user has received first B3, then it will add B3. If it has received first B2, then it will add B2. Another important challenge which comes here, it is a monopoly. Any type of monopoly need to be prevented, because a single user or a group of users should not gain the control. We don't trust anyone. Maybe the possibility comes here that a group of users, they control every time they are generating a block, they are solving a puzzle and they are adding a block in the blockchain. Suppose we are having 3 miners. This miner, when it is generating a block, and its block is being added to the ledger, then it may be possibility it is able to add only 4 blocks, where this particular is added 30 blocks, and maybe this has added 2. Now if you see the maximum time this particular miner is adding the blocks to the blockchain, so indirectly this person has gained the control over this blockchain. Asynchronous versus asynchronous. So we have already seen what is asynchronous, asynchronous. So just for the review part, so synchronous, it says I'm sure that I will get the message in the real time, and theoretically we say no delay or minimum delay, but still we face a delay issues due to the architecture of the network. Whereas asynchronous says I'm not sure whether and when the message will arrive. I have sent the message and I am not aware when the receiver will receive the message. Whereas in the case of the synchronous, we say that as soon as I send the message, the receiver will receive it. For example, when I am talking on a phone, then at that time this is a synchronous, because as soon as I started talking, the thing is being delivered, my speech is being delivered, my words is being delivered to the receiving end. So this is synchronous. And the asynchronous, for example, I am sending a mail, but I have sent the mail, but at what time the receiver will receive the mail, it depends upon the network. It is not on the real-time delivery. So this is asynchronous. Now the thing comes when we talk about the consensus protocol. So we are having n number of set of protocols in the blockchain available, both for the permissionless and the permissioned environment. So now the question comes, what the requirements, what we expect, what the blockchain architecture expect from these algorithms. The very first thing comes, these protocols should support low latency, that is, should have low latency delays or almost instant finality. High throughput, that is, the protocol should have high throughput, maximum amount of transaction being added in a single block. Robustness, the protocol should be robust. It should degrade the latency and throughput in the event of node or network failures. That is, if some node get failed, then again the network still operate as it is being operated earlier on. Trustless consensus, the protocol should enable the trustless environment. That is, the users, they don't need to be aware about the presence of other users. The puzzles or the encryption or any kind of cryptography techniques, if we are using here, it should be complex, but again, it should be easily verifiable. So the protocol should involve a computationally intensive task, which is very complex or difficult to solve, but once it is being solved, other users, they can easily verify the result. Fault tolerance, the consensus algorithm should be able to run in the presence of faulty or malicious nodes. That is, if some Byzantine nodes are present, still my consensus algorithm work. It should not fail. What are the Byzantine nodes? These are the nodes which are sending the false information about the network to other peer nodes. For example, if I want to add a certain transaction in the blockchain ledger, maybe this Byzantine node, it can convey that this transaction is not validated one, or it can say that it has been earlier added on. Some ambiguous kind of information it is sending, due to which that particular transaction, that particular block is not being added to the DLT. So if such kind of Byzantine nodes, they are present in my network, then again my consensus algorithm should have such power that it should still able to take the decision. Integrity, no node makes the decision more than once. The nodes make decision only once in a single consensus cycle. Termination, all honest nodes, they terminate the execution of the consensus process and eventually reach a decision. That is no infinite looping. That is, I want to make a decision, but I am stuck in an infinite loop. These are certain models or the algorithms which have been provided for the permissionless environment. We are having proof of work, proof of stake, round robin, proof of authority, proof of elapsed time, consensus model. Today we are going to discuss, our main focus is on proof of work. Before discussing the proof of work, let's discuss what are the failure in a network. We could have a crash fault, that is a node stops responding. We could have link fault. In the case of a link fault, the link, that is two nodes, they got disconnected. Byzantine fault, we have already seen the Byzantine node. So a node started behaving maliciously. That is a Byzantine fault. Before discussing POW, we should also remember the FLP impossibility. What this FLP impossibility says, it says consensus is not possible in a perfect asynchronous network even with a single crash failure. That is, it cannot ensure safety and liveness together. When we talk about the consensus algorithm in a blockchain, there are two terms which are generally being talked about. One is safety and another one is liveness. In the case of the safety and liveness, both together, they cannot go together hand in hand. If you focus on the safety, then liveness suffer, or if you focus on the liveness, then there may be possibility that you don't, your safety part got suffered. That is, you need to take there's a trade-off kind of thing between safety and liveness. Proof of work, the consensus algorithm, which is also known by the name Nakamoto consensus or a Bitcoin consensus algorithm, since in Bitcoin, the proof consensus algorithm which has been implemented is proof of work. In this algorithm, liveness is more important than safety. Immediate focus is on liveness with a minimum safety guarantee. Full safety can be ensured, but later on, with the time, full safety can be ensured. We will see later on this thing. Let's first have a look. What is the consensus model, proof of work consensus model? In the case of a POW, the user publishes the next block by being the first to solve a computationally intensive puzzle. There is a puzzle. When a block is being generated, there is a puzzle. All the miners, they receive this block, they try to solve that puzzle, and whoever, the miner who solved this puzzle first, become the leader of this particular block, and this block is being added in the DLT. The solution to this puzzle is the proof of their performed work, and moreover, when we got a proof, then this proof is verified by the other miners also. It is not just like a kind of thing that I have solved something, now I become the leader. Although I become the leader, but still the other miners, they would also validate that my proof is the sufficient proof, is the correct one. So the puzzle is designed such that the solving the puzzle is difficult, but checking the solution should be easy. The common puzzle method is to acquire the hash digest of a block header less than a target value. Common puzzle generally we say that this is the block which is need to be mined, and we find a hash value of the header of this block, and the solution, the answer which we are getting over here, we say that we are having some target and our answer should always be less than this target value. Now the thing comes that we are aware that the header block, the information is fixed, but there is a field through which we play the game, and that field is the nonce field. That is, we find the hash value of this and we continuously change this nonce value. Now whenever we are changing a nonce value, we are getting different hash values. On these different hash values which we are getting, we compare it with the target value and see whether we have reached to a answer. As soon as we reach to a correct answer, that is, we got a hash value which is less than the target, we say, okay, we have got a solution, and that particular miner become the leader. Now the adjustment to the difficulty target is done to ensure that the no entity can take over the block production, as we have already seen that what we say that one of the users monopoly, which we are talking about earlier. So this target value never remains the same. We keep this target value same for some amount of time, predefined time, and after that we change this target. So as an example, consider a puzzle where we are using SHA-256 algorithm, and the computer must find a hash value meeting the following target. And what's the target? We are saying that this is, let's suppose, our information which is present in the header block, and we are having a nonce. Nonce is also over there, but what we are manipulating here, we are manipulating this nonce value. We are combining these two things, running SHA-256 on this, and we are getting an answer. Now what is the difficulty or the target which we have set here? We say that we need to select the nonce in such a manner that the hash value which we are getting, it should contain 6 leading 0. Now this is the target I have set, and this target or the difficulty level I am changing with the time. For let's suppose if I am saying that it is 6, later on I could say it is 7 leading 0, and so on. Now see what happens. When we keep 0, we got this hash value. Again, this is not solved. We increment the nonce value by 1. Again, we got some hash value. And if we see, again, the answer is not matched. Now, we keep on going like this. Now, with this nonce value, if you see here, what is happening? We are getting the hash value where we are having 6 leading zeros. Now, our puzzle got solved. So, we will send this nonce value to all the miners to verify. They will verify the things. So, if you see, to come over here, it is a computationally intensive task. But once you have got the result, you have got the answer, you send this answer to other miners, and it is very easy. Within a fraction of time, the other miners, they can come to a common agreement that, okay, this is the correct answer. And that particular miner who has sent this answer, he becomes the leader. Now, to solve that earlier puzzle, it took about this much guesses. And it took around 54 seconds on a relatively old hardware. Now, each additional leading 0 will increase the difficulty by increasing the target by 1 addition. That is, instead of 6, if I am saying 7, with the same example, it is taking 1 hour, 18 minutes, 12 seconds. That is, with 6 leading 0, we are getting the answer in 54 by just increasing single digit. This is a drastic change in the computation. So, there is currently no known shortcut. We need to do the computation. We cannot adopt shortcut in this case. Publishing the nodes normally attempt to solve this computationally difficult puzzle to claim a reward of some sort. Usually the miner who becomes a leader, he got some bitcoins. The prospect of being rewarded for extending and maintaining the blockchain is referred to as, that is, it works on an incentive system. Once a publishing node has performed its work, it's sent. Other miners, they will validate it. Recipient full nodes verify that the new block fulfills the puzzle requirement, and they will add the block to their copy. In this manner, the new block gets quickly distributed throughout the network of the participating nodes. Verification of the nodes, as we have seen, it is very easy. For many proof-of-work based blockchain networks, publishing nodes tend to organize themselves into pools or collectives. Generally, the miners, they are coming together in a group, and they are being termed as pools or collectives. That is, for example, a group of miners, they come together at this node 1, node 2, node 3 and node 4, and they are working in parallel to find an answer. Suppose in node 1, he is checking the nonce from this to this. Node 2 may be checking the nonce from this to this, and node 3, that is, they are working in parallelly. So the following result which we have seen, it has found at this, and if we say this is being found by one of the node, that is the node 4, and since we are working in parallel, so the time got reduced. Dividing up the work amongst many more machines yields much better result as well as more consistent rewards in a proof of work model. So this is the working. So we are having a header. This is the field which we are changing continuously. Rest remains the same. So we are changing this header to this with some nonce value, and we are finding a hash value. If hash value is less than target, then we propagate the block to the network, to other miners to validate, to verify the things, and start mining the next block. If it is no, then we will try different nonce value. Again, this cycle is being repeated unless we got this answer. Security measures for POW. Cyber attacks, attackers attempts to fill the network with the clients under its control, create multiple identities. How the cyber attacks being carried out? Multiple public key addresses are there to control the network, and it refused to relay the valid blocks or relay the attacked block. This is the thing which the attackers under cyber attack do. This is the activity. Either they say, okay, this is not, they won't relay the valid blocks, or they will relay their own malicious blocks. So how in POW the solution is being provided by diversifying the connections. That is, Bitcoin allows one outbound connection to per 16 block of IP addresses. That is, miner, it cannot make both connections simultaneously. That is, it cannot make these two nodes simultaneously as their peer nodes. DOS attack, it is also being carried out on POW. It sends a lot of data to a node and block the processing power. How we can limit this? Limit the forwarding of the blocks or disconnect a peer that sends too many transactions. Maybe that particular node has become malicious node. So now the question comes, can we break the POW? The answer is, although it is computationally difficult, but it is not impossible. The attackers generally, they deploy high power servers to do more work than the total work of the blockchain. A known case of the successful double spending has been reported in POW in November 2013. It is being discovered that Hash.io mining pool appeared to be engaging in repeated payment fraud against Bitcoin Dice, a gambling site. You can find more information on this particular site. This is all about for today. So if we sum up this lecture, so we can say that today we have discussed what is a permissionless environment, what is the meaning of consensus algorithm. We have discussed what are the requirement or the challenges of a consensus algorithm in the permissionless environment. What are the what kind of solutions which we are going to design for all these challenges? What are the things, or what are the features they need to satisfy? Then we have seen few algorithms, and one of the algorithm, that is Bitcoin consensus protocol, that is POW protocol, we have discussed in detail. So this is all for today. Jai.